Hello friends, in this session we are going to talk about statically and dynamically induced EMF. Let's begin. Yes, starting about statically and dynamically induced EMF. Actually, this is a topic in which students get confused. Why? Because of standard books. Now, what is the problem with standard books? Let us understand. So actually, standard books say that at some point, standard book says whenever flux is maximum, EMF is maximum, voltage is maximum. And at some point they say that when flux is zero, voltage is maximum. At times, so what they say is that whenever flux is maximum, induced voltage is going to be maximum. At times they say that when flux is maximum, induced voltage is zero, or when flux is zero, voltage is maximum. This is the problem with the statically and dynamically induced EMF. So in this session, we are going to study both of them in detail, and at the end, I will tell you that both are same. Let's discuss. See here. See here. From Michael Faraday, we know that yes. Now we know one scientist whose name was Michael Faraday, right? Michael Faraday said that the induced voltage is going to be directly proportional to change of flux with respect to time, d phi by dt. That is what Michael Faraday said. Now, let me tell you one simple story. Actually, you want to know that this particular man, Michael Faraday, he is also known as father of electrical engineering. Yeah. Speaking about Michael Faraday is a very inspirational personality. Why so? Let us understand. Michael Faraday, at the age of 14, this man was not studying. I mean to say, he took only basic education. He took only basic education till the age of 14. And then what he did was, for next 7 years, he actually worked in a printing press for 7 years. For the next 7 years, he just simply worked in a printing press. Why? Because he was economically weak. Michael Faraday was very, very economically weak. He had no money. So in order to survive, for 7 years, this person worked in a printing press. Just imagine. He didn't even have high quality education. He simply had school education. That's it. Basic education. ABCDs. That's it. This person, can you imagine a person like him who only merely had some school education was able to find out this particular expression? Just imagine. One more thing, whatever knowledge he gained, that was because of this particular printing press only, because he used to read books, extra knowledge books here. So whatever knowledge he gained, that was with his working for 7 years only. No school education, not at all financially, economically strong. He was very, very poor guy, still he was managed. Now, this particular man, why he is called as father of electrical engineering? Let us understand that. This man, without having school education, being so poor, still in 1840, this man gave us the laws of electromagnetic induction. In 1840. Now you will say, sir, 1840, it's okay now, there is no problem. But you need to understand the time. 1840 was a time wherein atoms were not discovered. Just imagine, in 1840, this time nobody discovered even atoms. There was no point of having protons, electrons and all. There was no point of having charges. Still this person gave the complete, like, so now you just imagine, in 1840s, when atoms were not discovered, this man gave the complete theory of electromagnetic induction. Now whatever he said, actually see here, Faraday was a schoolboy, was a school kid. He did not even know what is education, engineering and all. He imagined this. He used to imagine this stuff. He used to imagine that, when you have, let us say, two charges here, like two charges, or for example, you have mass here like this, M1 and M2. Masses are there. Then he was the first person who said that, yeah, Newton said that there will be some force existing between these two. Right? Now, Faraday, he was the person who said that, but force acting is instantaneous. But no, he said that no, force will not be instantaneous. There is going to be some space in between here like this. So whatever force is applied by, let us say, M1 on M2, that will move through the space, through this space. This is called as medium. Just imagine, he thought, see, he was the person who opposed Isaac Newton for that. He is the person because of whom we today have theory of relativity as well. Yes, we know that Einstein said, relativity and all, he explained those concepts, right? Special theory, generalized theory, right? But still, the main foundation was given by Michael Faraday. Michael Faraday was a genius. Anyways, let us move forward. Yeah. So from Faraday, what we know, he said that whenever there will be a conductor under influence of changing magnetic field, EMF is going to get induced in that conductor. That is what he said. So let us say the EMF induced is proportional to, he said, d phi by dt, which means whenever there will be change in flux with respect to time, EMF is going to be induced. That is what Faraday said. Now for instance, you have flux like this, let us say. Let me draw some flux on this graph. Let me say this is flux phi. Let me have a sinusoidal flux distribution. Let us assume that we have a sinusoidal flux distribution. Now, see here. What will be the voltage EMF induced? d by dt of flux phi. d by dt of flux. Right? Which means, if flux is sinusoid, now we know that derivative of a sine wave is what? Let us say it is sin t. It is going to be cos t. Derivative will be cos t. And we already know that the waveform of cos will be like this. Right? Waveform of cos is like this. Let us say this is the induced EMF E. Now, here if you see what is happening, see here. Whenever flux is maximum, see, blue is my flux, right? Blue is the flux. Whenever flux is maximum, EMF is going to be 0. EMF is going to be 0. And whenever flux is 0, see here if you see, this is flux, here flux is 0, here if you see, here flux is 0, EMF is going to be maximum, red is EMF. So when flux is 0, EMF is maximum. Right? This is, let's say, case 1. Now see here. Now we have also studied somewhere that EMF is nothing but BLV. What is BLV, sir? See, V is the velocity of the conductor in meter per second. Velocity of the conductor in meter per second. L is the active length of conductor. Right? And B is the flux density. Right? Now, if we see here, if for instance, this active length of the conductor and this velocity, if I am assuming as constant. So, from this what we get? So, from this what we get? EMF is nothing but proportional to B. Right? EMF induced is nothing but proportional to B, which means EMF is proportional to flux. Can I say that? You ask me how? See here. See here. We know that this is flux density B. What is flux density? Flux density is nothing but flux per unit area. Right. Let me assume for a given area, or we can say area is constant, my flux density will be proportional to flux. So, can I say that in this case we are saying E is proportional to flux? Which means, see here. Yes. Now, from this particular relation, what we understand? Let me have flux here like this. Sinusoidal flux. Let me have sinusoidal flux. Now, from this if we see, what is written? EMF is proportional to flux, which means EMF will be, let us say, like this. EMF in volts. Now you will ask me, sir, you can actually take it equal to also, no? See here, you need to understand one thing. This flux is in Weber. Units are different. This flux is in Weber and EMF is in volts. Their units are different. Right? Now see here. Remember that, because if their units are same, you can basically compare them. But since their units are not same, means one is, let us say, in centimeter and other one is, let's say, in grams. If you see, centimeter means distance, gram means weight, right? So both of them cannot be compared, right? Now see here, basically what we have understood here, that if my flux is like this, then whatever my flux is, whatever way my flux is, the same way EMF is going to be there. Means they are going to be in phase like this. That is the meaning of E is proportional to phi. Now, what does this mean? See, this means that whenever flux is 0, EMF is 0. Whenever flux is 0, EMF is 0. Whenever flux is maximum, EMF is also maximum. That is my point, right? Whenever flux is 0, EMF is 0. Whenever flux is maximum, EMF is maximum. So, let us write. Flux is maximum, EMF also maximum. When flux is 0, EMF is 0. Now see here. See these two conditions. See these two conditions. One says that whenever flux is maximum, EMF is 0. Whenever flux is 0, EMF is maximum. Whereas here if you see, whenever flux is maximum, EMF is maximum. And here if you see flux is 0, EMF is 0. Aren't they contradicting? Aren't they contradicting? See here again, one more time. Faraday says that whenever flux is maximum, EMF is 0. Whenever flux is 0, EMF is maximum. From this equation of BLV, see, we have studied this BLV, especially in DC motion we have studied. Right. See here, If E is equal to BLV, if we see, then from this relation we have got that E is proportional to phi, which means when flux is maximum, EMF is maximum, and when flux is zero, EMF is zero. What a contradiction. Now see here. So will you say that this is right, this is wrong, or this is right, this is wrong, or you can say both are right? What will you say? Because Faraday, follow Faraday. Faraday gave only one equation. This one, where it is? Yeah. Faraday said that only EMF is proportional to d phi by dt. Rest everything we people have discovered like this. You know, this stuff, BLV stuff and all. Faraday only said E is proportional to d phi by dt. That's it. He didn't say anything else. He only said this much. Right. So who is right? Is this right or this right? Both are right. And this one is called as statically induced EMF. This one is called as statically induced EMF. And this one is called as dynamically induced EMF. Now, I hope you have understood the contradiction. I hope you have understood what is the problem, why studying statically induced EMF and dynamically induced EMF is difficult. We have understood it right now, because this is a problem. One says that when flux is maximum, EMF is zero. Other one says when flux is maximum, EMF is maximum. Someone says that when flux is zero, EMF is maximum. He says that if flux is zero, EMF is zero. This is a contradiction, and we are going to understand this contradiction in detail right now. Let's see. Yeah. Let me have two cases at first. This is, let us say, case 1. Case 2. See, very important. Yeah. We know that this is the structure of transformer, right? Now, if I supply AC here, what is going to happen? Flux will be formed here, right? We have already studied this in transformer. Flux will be formed phi, and the moment this AC, the moment my supply voltage is alternating, flux is also going to be alternating. Already we know that from transformers, we know, right? If this voltage here, if it is sinusoidal, flux is going to be sinusoidal. Now, see here, the moment flux is sinusoidal, what does that mean? See, let us say that at start current was flowing like this, I. In the first half cycle, current was flowing like this. So if it is moving like this, which means flux is going to be this way. Let me draw here, see. This is current, let us say. This is current, I1. I1. See here, very important. I1 current, if it is sinusoidal, right? If it is sinusoidal, for time being I am saying that it is sinusoidal. It is because peak is sinusoidal on, we will see later. When time comes in transformer, I will discuss. But right now, for time being, let me say that it is sinusoidal. For time being only, let me assume that it is sinusoidal. Now, see, if it is sinusoidal, which means in the first half cycle, this one, in the first half cycle, what is going to happen? This flux which is there, this flux will move like this, because this is current, right? Current, like this. Flux is going to be shown by thumb. This is going to be the direction of flux. Now, then it is increasing, then it becomes zero, right? Now it becomes negative maximum, which means this current direction is now reversed like this. Current direction for the second half cycle, the direction of current is going to be reversed. The moment it is reversed, what is happening? Current is moving like this, which means this is going to be the direction of current, this. Right? The moment this is the direction, which means flux is going to be downwards. So here, flux will be downwards, like this. Which means downwards means here it will be like this. Now, if for example, I am sitting inside the core. I am sitting inside the core here. This is very important point. I am sitting inside the core. What will I experience? At some point, flux is going to be 0. Then it is going to be positive maximum. Again 0. Negative maximum 0. Positive maximum 0. Negative maximum 0. Positive maximum here. Similarly, here also if you see 0. Positive maximum 0. Negative maximum 0. Positive maximum 0. Negative maximum 0. Which means I am sitting here on the core, I will be experiencing some change in flux. Right? The moment I am experiencing some change in flux, what did Faraday say? E is proportional to d phi by dt. Right? The same change will be experienced by these conductors as well. The moment these conductors are in influence of change of magnetic field, change means 0, 0, positive max, 0, negative max, 0, positive max, right? The moment these conductors are experiencing the change in magnetic flux, what is going to happen? EMF is going to get induced in these conductors. So let us say this is EMF here like this. It is E2, we know that. Let us see. Now next, let me consider second case. Yeah, see here. What is happening? See, yeah, see here. In the first case, what we did, in the first case, our, what do you say, primary winding, it was directly connected to AC supply. Now what I am doing, this winding I am connecting to DC supply, let us say. I am connecting to DC supply. Now, what is this structure? This is a transformer structure only. Just the primary is mounted on this rotor shown by blue. This is the rotor, right? This is the rotor, which means it is going to rotate after some time. See here, what is happening? The moment current flows here, I current is flowing, which means current is flowing in this direction. Which means by using right hand thumb rule, what will I get? I will get the direction of flux, which will be like this. From this part, if you see, flux is outside, which means this will become north pole and this will become south pole. Am I right? Upper portion will be north pole, down portion will be south pole. If you see here, it is moving like this, so flux is going to go like this. This is going to be, let us say, flux phi. Now, what I am doing, I am going to rotate this rotor. Rotate means, sir, see here. I am going to rotate this rotor by 90 degrees, let us say. When I rotate it by 90 degrees, what is going to happen? This rotor will look like this. Right? The moment this is rotated like this, the moment this rotor, see here, this supply is DC. Remember, here this supply is DC. The moment I rotate this rotor, this N will shift to here and this S will shift here. N was here. This was N. This was N. This was S. N got shifted here. S got shifted here. Am I right? Now see here what is happening. This is north pole and this is south pole. Now if you think of flux, if you see, flux is going to be how? See, outgoing from north, incoming to south, which means flux is going to be like this. Flux is going to be like this, which means in this condition there will be no flux moving through the core. Flux is going to be 0 in this case. Now I am rotating it furthermore like this, means initially it was like this, now it is like this. In the second condition, what we saw, in the second condition we saw that flux through the core is 0. Flux through the core is 0 in the second case. First case, what we saw, this is north pole and south pole, flux is going to go like this, complete its path. In the second case, what we saw, this north pole shifted towards right, south pole shifted towards left like this. And now here in this case, if you see, flux is moving out from the north, but it is completing the path here only. It is not moving through the core, which means in the second case, flux is 0. Now, what is in third case? Let us see. In the third case, let me assume that this rotor is rotated like this. Further rotation is in this direction, means this north will come here now and this south will go up here. Now the moment this happens, what is going to happen? See, this north flux will go like this and it will complete its path like this, means this is going to be the flux. In the third position, flux is going to be this. Come on, see here, in the first position flux was like this. In the second condition, flux was 0. Red is second condition, flux was 0. In the third condition, since this is north, this is south, north. This became north now, right? The moment this becomes north, flux is going to come out of the north like this and it is going to complete its path through the south pole, which means the flux is going to be outwards. Now, if I am sitting on the conductor, see. Now see, if I am sitting in this core, this is me, I am sitting inside the core. Inside the core, if I see, if I am sitting here, am I going to experience the change in flux? Of course, because if this is rotating like this, which means, see here, concentrate. In the first case, flux was in this direction. In the second case, flux was 0. In the third case, flux was in this direction, which means 0, positive max, 0, negative max, 0, positive max, 0, negative max, means the same condition will happen here. Here I will experience a change in flux, which means this particular coil or this winding will also experience a change in flux, and that I will get here. Yes, so now if you observe, in the second case also EMF is going to be induced. Why? Because I am experiencing the change in flux in the core, means the flux flowing through the core is changing. That is the reason I am going to get a EMF there also. Now you please tell me, what is the difference between these two diagrams? Nothing. This is also a transformer, this is also a transformer. EMF is induced here also, EMF is induced here also. But there is only one difference, that this is called as, the EMF which is induced here is called as statically induced EMF. And the EMF induced here is called as dynamically induced EMF. Now next, what are we going to do? We are going to extend the discussion which we did in case 2 here in case 3. We will extend the discussion. Let me have case 3. Yeah, let me have the same transformer like this. Right, let me have a rotor here. And yes, in the first case of case 2, means this was case 2, in the initial condition we saw that, see, N pole was here, S pole was here, right? N pole was here, S pole was here, blue. The same I will describe here, the first condition I will take here, the first instant, NS. Yes, the first instant, NS. This was N, this was S. Now, we know that here in the second case, what we did was, we rotated it in the clockwise direction like this, so that N comes here, S comes here, which means this north will come here, south will go there. So let me have another this structure like this. It is the same rotor, right? It is the same rotor, see. So this becomes north now and this becomes south now. Now, see here. For the first case, we know that when here, if you see blue case, north. If we talk about the blue case, we see that this is north, this is south, which means flux is moving in this direction. Everyone agrees with me? Right. Now, how much is the flux flowing through the core? Very important. Mark my lines. What is the flux flowing through the core? Maximum. Maximum in this direction. Means flux, I am writing this, flux flowing through the core is maximum. Flux flowing through the core for the case of blue is maximum. What about red? Already we have seen, north is here, south is here. Flux is going to pass like this, means it is going to complete its path like this, from north to south like this, right? Which means, in the second case, that is red condition, flux flowing through the core is 0. Right? Now see, let me recall. What did Faraday say? See here, concentrate. Faraday said that if this is flux like this, already we have discussed this, if this is flux and I want to show induced EMF, then induced EMF is going to be cosine waveform. Why? Because it is the derivative of sine. This is going to be the cosine waveform. From this, what we understood, whenever flux is 0, induced EMF is maximum. And whenever flux is maximum, flux means blue. Whenever blue is maximum, red is 0. Which means, whenever blue is maximum, red is 0. Red is what EMF? EMF is going to be 0 in this case. Right? And in the second case, if you see, flux flowing through the core is 0. Whenever flux flowing through the core or through the coil is 0, flux flowing through the core is 0. Zero flux, yes, here is 0 flux. Whenever flux is 0, EMF is maximum. Negative maximum, positive maximum doesn't matter, but EMF is maximum, that is what matters. See, so in the second case, red, EMF is maximum. Why? Because we have already seen north, south. In the first case, blue is there, flux is going to be maximum. The moment flux is maximum means EMF is 0. EMF is 0 means EMF is 0 written. Next case, red. N is here, S is here. Flux will pass through this area only. Flux will pass like this only, from north to south like this. No flux will be moving through the core. The moment flux flowing through the core, mind my words, flux flowing through the core is 0, which means EMF is maximum. No. What about BLV? But if we talk of EMF is proportional to flux, already we have discussed. This we got from BLV, right? We got this from BLV. So now if you think of, you will say, sir, but from second one, if you see, whenever flux flowing through the core is maximum, EMF has to be maximum. And whenever flux flowing through the core is zero, EMF has to be zero. But what can be done? What is the solution? See here. What happens in a transformer, let us discuss. Because now you will actually understand. Now you will understand what is the meaning of a coil, what is the meaning of a coil side, what is the meaning of turn. You will understand it right now. See, when we talk about transformer, right? In transformer, you tell me all are active lengths, no? What we will do, let me take another case and then we will compare third case with the fourth case and then try to understand it. That will be in a simplified form for you. It will make you easy. Let us see. Yeah. Now, let me have a stator like this. Right? This is a stator. Bullseye. Now, let me have two stator conductors here. Conductor 1, conductor 2. See, two conductors are there placed on a stator. Now let me have a rotor. Now, see here, we are going to extend the same thing which we discussed in case 3. Let me tell you how. This is the rotor here. Do you agree? Now, I am taking the same rotor here. Means, in the first case, in blue case, this is north and this is south. And I am assuming that this rotor is going to rotate in this direction, in the clockwise direction, and then next it will have N pole here, S pole here. Right? Let me have that. Yeah, so let me have this here. This is going to be north pole, this is going to be the south pole. This is basically the same rotor, right? This is not a 4-pole machine. This is a 2-pole machine only. This is the first case of the rotor. This is second case of the rotor. First position of the rotor is blue. Second position is red. Same here like this. Right? Now, these are the conductors here. Basically, it is a coil, right? It is a coil. Now see, very important thing. This is the coil, right? Let me have only this part here separately. Right? And from here we had this flux, right? We had the flux here like this. Right? Now, let me tell you one thing. See, when I talk about a coil, can I show the coil like this? Conductors like this only? Means basically, can I show it like this? They are nothing but conductors. And the conductors. Now, let me take these two conductors here. One conductor is this one. Another conductor is this one. Same conductors, right? These are the same conductors which are taken there. These are the same conductor. This conductor is taken here, this conductor is taken here. That's it. And now I have the rotor. Now, see. Now if you see, this is north pole, right? This is north pole and south pole. This is the first position. In the first position, what we got? Flux flowing through the core. Flux flowing through the core is maximum and EMF is 0. Let us see if it is working here. This is the coil, right? Concentrate. This is the coil, right? For example, if this conductor is X, this is X dash. So this has to be a coil. How it will be a coil? Let us see. This will be represented like this, right? These are the coil sides. This is coil side X, and this one is coil side X dash. And here I will have a back-to-back connection. Back-to-back connection like this, right? And then these are the terminals out, which are nothing but these terminals which are shown. These are those terminals. This is X and this is X dash. This is going to be a coil. Now, for example, this is X and it is X dash. See here, this is X, this is X dash. Same coil is shown here in this particular fashion. Now, if you see how much is the flux through the coil, again, how much is the flux through the coil? This is the coil. This is the flux through the coil. See, this is the coil. This is going to be the flux through the coil. If you see here in the first case in blue, if you see coil, flux flowing through the coil is maximum. Flux flowing through the coil is maximum. That is the reason, what are we saying? Flux flowing through the coil is maximum. This is the coil. Flux flowing through the coil is maximum, which means EMF is 0. So, is there EMF 0? You will not understand this unless and until I will discuss a small thing related to a bar magnet. Let us see. See here. For example, you have a bar magnet here like this. This is north and this is south. Right? Or let us say, I have let us say 2 poles here. One is N pole and one is S pole here like this. Right? Let us say I have 2 poles. One is N pole, one is S pole. Now see here what is happening. If you think of the MMF, see, in this axis, flux is maximum, right? North to south, flux lines will flow, maximum flux lines will flow. And in this axis, at the center, flux is going to be 0. You tell me, sir, how flux is 0 there at the center? Basics. These are the basics. Plus standard basics. See, if I am sitting here, if I am sitting at this particular point, let me draw a circle here like this. Let me draw a circle like this. Now, if I am sitting here on this particular point, I will experience maximum magnetic flux. The moment I move here, I will experience some magnetic flux. Some. The moment I go here, I will experience 0 magnetic flux. The moment I come here, I will experience some magnetic flux. The moment I come here, I will experience maximum magnetic flux. The moment I come here, I will experience some magnetic flux. The moment I come here, magnetic flux experienced by me will be 0. Here, if I am standing here, the magnetic flux experienced by me will be 0. If I am standing here or I am sitting here, magnetic flux experienced by me will be 0. If I am sitting here, magnetic flux experienced by me is going to be 0. Right? Now, this can be shown with a small diagram. Let us see. Yeah, see here. For example, if I have a north pole and I am considering sinusoidal flux distribution. I am considering sinusoidal flux distribution. See here. When I am near the core, when I am near the pole, flux will be maximum. The moment I go here, flux will be 0. The moment I come here, maximum flux is 0 here. For south, if I see for south, what is going to happen? Flux will be in opposite direction like this. For north, it will be, let us say the flux distribution is positive here. Then in case of south, flux distribution will be negative. You will ask me why? Because if you see, from north if it is outgoing, then from south it is incoming, right? Which means they are opposite to each other. That is the reason their flux distribution should also be opposite to each other. I hope you are getting this point, right? Come here. Yeah. Now, see here. See. See here. This is the North Pole. Yes. Let me consider the first case wherein rotor was in this direction. North and south was the rotor, like this. This blue. In that case, for north I will have flux distribution like this. Am I right? And for south also, I will have some flux distribution like this. And at the centers we know, flux is going to be 0 for the North Pole. Right? At the centers, flux is going to be 0. I am talking about the blue condition. See, just imagine that this particular red portion is not there. Just imagine. For time being, let us only concentrate on blue. Just think that this particular red portion is not there. Red portion is not there. There is only blue. What is going to happen? Flux will be flowing like this. Flux will be going like this. Right? North to south. North to south. North to south. North to south. From this particular discussion, we have understood that the flux distribution will be like this for north, and here the flux will be 0, here the flux will be 0 because it is the central axis. Central axis flux is going to be 0. Am I right? Now, what will happen here? See, the moment here flux is 0, here flux is 0. Now, observe here. Let us consider BLV case. BLV case, what we know? We know that EMF is proportional to flux, which means if flux is maximum, EMF is maximum. Right? Now see here, what is going to happen? This particular conductor for blue case means north is here, south is here. For the blue case, if I see this particular conductor, what will happen to this conductor? Here if you see, this conductor will experience 0 flux. Getting my point? This conductor is experiencing 0 flux. Yes, flux through the coil is maximum. Flux through the coil, see, this is the coil. Flux through the coil, this is the coil, x dash. Flux through the coil is maximum, but flux influenced by this conductor x dash is 0. Here also if you see, flux influenced by conductor x is 0, which means if flux is 0, then EMF is also 0. Flux influenced by this conductor is 0, which means EMF is also 0. Again, see here. This is x dash. This is the coil. Back to back connection. This is x dash, this is x, right? This is the coil. Now, flux through the coil, maximum. Flux through the coil is maximum. Flux influenced by this conductor, 0. Not getting my point. See, again. X dash. Flux through the coil, maximum. Flux through the coil is maximum. In that case, what is happening? EMF is 0. Another version, see. This is coil, x dash. Flux through the coil is maximum, but flux influenced by this coil side is 0. Flux influenced by this coil side, remember my word, see here, see. Again. This is x dash. Flux through the coil is what? Maximum. That is the reason flux EMF here is 0. In this particular case, if you see, this is x dash. Flux through the coil is maximum. In blue, flux through the coil is maximum. Through the coil is maximum, but flux influenced by this conductor. Again, flux influenced by this conductor is 0. That is the reason EMF is going to be 0. So in this case, if you see, when flux influence is 0, flux influenced by the conductor is 0, EMF is going to be 0. Yes, now let us think of the red case. Let me erase this. Yeah. Let me think of this second case when this north pole is now rotated to this position and this south comes here. Right? Second position means red position. red position if you see, this is N, which means the flux distribution for this red will be like this. The moment the flux distribution is like this, what does that mean? See here. This is the coil. These are the poles. Pole is like this now. See. Coil X dash. This is the pole. Right? How much is the flux through the coil? 0. This is the pole. This is the pole. This is X dash. This is X, right? See here. This is X dash. This is the pole. Now, how much is the flux through the coil? Through the coil, how much is the flux? 0. Again, one more time. This is X. This is X dash, right? Now, this is the pole. How much is the flux through the coil? 0. Because flux is like this. Flux will be like this. Flux will not be like this. Flux will be in this direction. Flux will not be in this direction, right? So flux through the coil is 0. The moment flux through the coil is 0, which means EMF is maximum by Faraday. Now, let us prove the same for BLV. This is coil X. This is X dash. This is the pole. This is the pole. This is my pole. Now, if you see, here is N, here is south. Here is north, here is south, right? This is the pole. Now see here. What is going to happen? What is the flux influenced by this conductor? How much is the flux influenced by this coil side? Maximum. This particular coil side or this conductor is under influence of this flux maximum. Which means here flux interaction is maximum. Rather, flux influenced by this conductor is maximum. So EMF is also maximum. Now, see here. Let me conclude. If we talk about a transformer, and here is the rotating machine, let us think one more time. See here, coil X dash. First case means blue, NS. In the first case, if you see, what is going to happen? First case, this is NS, this is N, this is S. Flux is maximum in this direction. Means flux through the coil is maximum. This is coil, this is X dash. Flux through the coil is maximum. Whenever flux through the coil is maximum, EMF is going to be 0. Now, for the same case, if you see, this is X dash, right? Now, flux through the coil is maximum, but flux influenced by this coil side or this conductor is 0. That is the reason here we can say EMF is 0. Moral of the story. Concluding part. See. Now, the most important part. Sir, we understood case 3 as well as we understood case 4. But the problem is when to use BLV and when to use Faraday. When to use E is proportional to d phi by dt and when to use this one. Let us see. See, very simple. E proportional to d phi by dt. E proportional to d phi by dt is valid, or we can say is used in case of coil or a turn. Why? Let us see here. See, in case of transformer, if you see, what is going to happen? In case of transformer, it is a coil, right? Means every inch of this coil there will be induced EMF. I hope you are getting it. One more time. See. Focus. In case of transformer, this is a coil. And this particular coil will be influenced by the change of magnetic field. Means every small part of this winding of this coil is going to experience the change in flux. Which means in each and every part of the coil there will be EMF induced. Right or wrong? In every part of this coil EMF will be induced. Means the whole length of my winding in a transformer is going to be active length. Active length means EMF induced. Whereas, come here. In case of a coil, if you see, this is a coil, this is X and this is X dash, and this is nothing but back-to-back connection. The moment this is back-to-back connection, will there be any induced EMF in this back-to-back connection? No. See, whenever we have a rotor like this, for example, I am the rotor. This is going to be conductor X. This is going to be X dash. Down from which, what will come? Back connection will come. Again, see. Let me tell you in simple words, see. This is a coil, this is X and this is X dash, right? This is a coil side X. This is another coil side X dash, or we can say this is conductor X, or we can say this is conductor X dash. Now you please tell me, in case of a rotating machine, will there be EMF induced in the coil or it will be induced in the conductor? You will say both. EMF will be induced in coil as well as in conductor. But let me tell you one thing, this back-to-back connection which is there, this is not in influence of magnetic field, which means this here there will never be induced EMF. In this part, induced EMF will be 0, which means you have to consider the conductors separate. This is X and this is X dash, and then you do the connections back to back. And for this particular thing, what we are saying is, whenever flux is maximum, whenever the conductor or the coil side, I am repeating, whenever the conductor or the coil side is influenced by the magnetic field, EMF is going to be induced. Means see here, in case of red, if you see, in case of red, what is happening? In case of red, if you see here, this conductor X dash and this conductor X, let me draw it with blue, with red, and this conductor and this conductor will be in the influence of magnetic field. They will be in the influence of magnetic flux. Now the moment this particular conductor is in influence of magnetic flux, EMF is going to be induced. Now EMF will be induced for this one, EMF will be induced for this one as well, and then they are back to back connected. Whereas in case of transformer, already they are connected like this. It is the same winding, right? There is no back to back connection here. All lanes are active lanes. In every inch and inch of this winding, EMF is going to be induced. Now, see here. What is the moral of the story? Moral of the story is, E proportional to d phi by dt, we have to apply only when we are thinking about a coil or a turn, and E proportional to flux we have to use in case of coil side or conductor. I hope it is clear. It may happen that you may not understand few things now. It may happen. There may be a small friction, but you need to watch this entire video once again. Then you may understand what I am saying. Now, please note this down, because understanding statically induced EMF and dynamically induced EMF is very important in case of rotating machines especially. So, again repeating, final conclusion. See, EMF induced d phi by dt, E proportional to d phi by dt is used only when we are talking about a coil or a turn, and E proportional to flux is we are going to apply it only when we are talking about a coil side or a conductor. Yes, so now let me tell you one thing. Some people may think that, sir, what is the meaning of a coil, what is the meaning of a turn, and what is meaning of a conductor and coil side? Let me tell you in very simple words. See, let us say this is a stator or a rotor of any machine. For example, you have here one conductor, another conductor here, right? Now, what is happening? See, if for example, I am saying that this conductor is X and this conductor is X dash, right? Now, so this will be indicated Now I can show this in this way. Let us see. Let me show this conductor X like this, and let me show this conductor X dash like this. Okay, and they will be back to back connected from the back. X dash, back to back connection, right? From the back they will be connected. This is called as overhang or back to back connection, right? We have already discussed about it. Overhang or back to back connection. Now this X, this is one single conductor, this is one conductor, right? See here, see, only this X, this is one conductor, so this is called as a conductor, or it is also called as coil side. This one single, this is called as a conductor or a coil side. Similarly for X dash, this one single conductor is called as conductor or a coil side. Conductor or a coil side. Now these two together, I am repeating, these two together means two conductors together with some back-to-back connection or some connection are called as turn. Means basically, see here, one turn will have two conductors. This is one single turn, this is one single turn, X dash, one single turn. It will be having two coil sides. This is either a conductor or a coil side. This is called as conductor or a coil side, and these two together will be called as turn. Now if there are many such conductors, see, now if there are many such conductors like this, many more, and then you have a connection here, then it will be called as a coil. Means a coil will have many turns. See, I am writing here. Means, see here one more time, one conductor is also called as one coil side. One conductor also called as one coil side. Two coil sides. Two coil sides means like this, X dash. They form one turn and many turns form one coil. Means one coil will have many turns, one turn will have two conductors or two coil sides. That's it. Thank you.